All right, I already talked about arithmetic series in the last one, but today I'm actually show you the proof for it. So it's the first time you've ever seen a proof of actually why this is what it is. But first, let's cover the basics. The title is Arithmetic Series, and we have 7 sort of ideas to get through. So if I wrote down just this particular sequence, I'd have 6, 9, I don't know, 12, 15, and then 18, and then I stopped right there. This would be called a finite arithmetic sequence. Okay, why is it finite? Yeah, it stops, right? Has a beginning and an end, right? Why is it arithmetic? It's increasing by the same value. What is that value, by the way? 3. Okay, good. And it's a sequence, okay? Now, what if I did this? If I did 6 plus 9 plus 12 plus 15 plus 18, I put a box around there and stopped it there, this would be a finite. Why would it be finite? Because stop, same thing, right? It's finite. It's arithmetic, right? Arithmetic. I'm just abbreviating that word. It's no longer a sequence, though. It's what we call a series, all right? So what's the difference between the word sequence and the word series? What's the difference? In a series, what are we doing? We're doing something. We're adding it all up, right? It equals a sum, right? In a sequence, we're just stringing them together, kind of like you were saying. In a series, though, we're adding them all together. Okay, what if I gave you this? If I gave you 6, 9, 12, 15, 18, and then put these 3 dots after it, what would that imply? Yeah, so what this would be an infinite arithmetic sequence, right? And you can guess what this one's going to be. 6 plus 9 plus 12 plus 15 plus 18 plus dot dot dot. That dot 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 implies that it goes on forever. So that'd be an infinite arithmetic series, right? Okay, so these are the basics. And today, you guys, our focus is going to be on this one over here. Why do you think that's going to be our focus? Why are we focusing there? Well, yeah, we've done sequences before, but could you add up could you get an actual number for an infinite arithmetic series? No, it keeps going forever, right? There's no end to it. There's no cap. Well, does that go to infinity? Like, what does that go to, right? So today we're going to focus on this one because we can actually put an end on it and put a cap on it, right? So that's our goal for today. So the sum of a finite arithmetic series. This is what we're working on today. All right, I'm gonna present it in a certain way that may look familiar to you, and I'm gonna go blue. All right. So let's talk about that one. I had 6 plus, what was it, 9, then it was what, 12, and then what, 15, and then it was what, 18? Okay, can someone add that up really quickly for me? Tell me what you get. Hank says 60. Can somebody else independently verify? Nick says 60, yeah? Everybody else agree? Okay. All right, so we say this is 60, all right? So I want you to think about this. 6 is the first term, right? And then we are adding the difference a bunch of different times, right? In fact, we're doing it 5 times. So 9 is just the first term plus a difference, right? 12 is just the first term plus 2 differences. Do you guys agree with that part? Yes? Yeah, Rich says yes. Okay. Now, what happens if I think about it a different way here, right? What if I start in the back and I subtract off my differences? Right? If I start with 18 and I subtract a difference of 3, what would I get? Yeah, 15, right? And then what will the next term be? 12, and then what will the next term be? 9, and then what will the next term be? 6, and hopefully that still adds up to how much? 60. Yeah, hopefully that still adds up to 60, right? We need that to add up to 60. Okay, we good so far? Not blowing you guys away? All right, so what we're going to do now is what we did before. We're going to add this thing vertically. We're going to add both sides of the equation vertically and see what we get. Okay, 6 and 18, how much is that? 24. 9 and 15, how much is that? 24. What, are these all 24? Well, that's crazy. They're all 24. Okay, 24. And then if I add the other side, I get what? I get 120. Okay. All right. How many 24s do I have? I have 6. Oh, I have 5 of them, right? Does it make sense that I have the same number of 24s as I have in my sequence? I have the same number of 24s as I have in my sequence, right? So I have a grand total of 5 24s. You guys agree with that? And it's still equal to 120. Everyone on board still? Okay, well, I'm gonna rewrite the number 24, right? 5. 24 is any one of these combinations that I like, so I'm gonna do a 6 plus an 18. And then I'm gonna rewrite the number 120 as 2 times 60, because remember the answer that we were looking for in the beginning, you guys, was 60, right? So there must be a better way of doing this. I'm developing something here. All right. I wanted to get 60 over here, so I better divide everything by 2. Everything by 2. All right, now we have something that's really good for ourselves here. Let's take a look at this. What does the 5 represent? Number of what? Number of terms, right? We usually call that n, right? What does the 6 represent? The very first term, we call that a sub 1. What does the 18 represent? The very last term, right, which was a sub n, right? And then look, we had it divided by 2, and that's equal to the sum of the first n terms. All right? So this formula right here, this is a very, very useful, important formula. This allows us to add up a finite arithmetic series by just knowing the first, last term, and total number of terms. Okay? Yeah, the sum of the first n terms. The sum of the first n terms. So here's the actual proof that it is true that the sum of the first n terms is equal to n over 2, the first term plus the last term. So I'm going to introduce this to you. Remember, this is our goal right here. Okay? That's our goal. All right, so here we go. Everybody agrees that the sum of the first n terms is just the first term plus the second term plus the third term plus, how long would I do this, you guys? Yeah, a sub n, right? Everybody agrees with that part? No one blown away yet? We're all on board? All right, cool. Well, I could rewrite this like this. S sub n, that's just the same thing as the first term. I could rewrite the second term as just the first term plus a difference, right? You see that? Because the second term is just the first term plus one difference. You guys still with me on that? What will the next one be? The first term plus two differences, right? Plus all the way up, what would be the very last term? Well, it would be the very first term plus n minus 1 differences, right? Do you guys see that? And doesn't it make sense to us that a sub n is defined this way? Because after all, that is the explicit form of that. So that makes sense. All right. Well, now we come to this part in the proof. What did I do here in this line? I just wrote it all backwards, right? You still with me on that part? So watch, here we go. If I write this backwards and I subtract off my differences, well, it's the same sum. It would be this. It'd be the very last term, which is an, plus an an minus a difference, plus my an minus 2 differences, plus all the way out until I got to what? The very first term. Okay? Oh, absolutely. I'm going to add these vertically, and something really cool happens, and that's the part I want you to see. I want you to add up these last two. Okay? How much is Sn plus an Sn? 2 Sn's, right? Equal. Now, if I pair this one up, what would I get? I would get an A1 plus an AN. You guys agree with that part? Okay. Now, pair this one up. What do you guys get? Yeah, what happens to those D's? Those D's cancel out, right? So what would I be left with? Yeah, where'd my green pen go? Yeah, I would get another, right? I'd get another A1 plus AN. In fact, what would that happen? That would happen all the way out, right? So I'd end up with just, the last one would just be A1 plus A sub n, right? Well, how many of these do you have? We don't have infinite. It's a finite series. It's a finite series. How many do I have? I have n of them, right? Very good. So there's a better way to write that. I would get this. 2 S sub n is equal to n times, well, I have a sub 1 plus a sub n, right? But do I want twice the sum? What do I want? Divide by 2. Divide by 2. No. So it's the proof, right? So there it is. S sub n is equal to n over 2, the first term, a sub 1, plus the last term, a sub n. And that's what we were supposed to show. Yeah, so if I finish it out, I forgot to write that part in there. But when you add vertically, you would still end up with an a1 plus an. Yeah, here we go. Okay, here's an example where we could use this. If I want to take the first 250 positive even integers and add that up, how much is that worth? Plug in the equation, right? So let's actually write this out. So what will be the very first term of this series? 2, absolutely. What's the next one? 4, good, yeah. What's the next one? 6, right? So here we go. This is the very first term. This is the second term. This is the third term. And I'm going to keep going until I end up with what? 250. So a sub 250. Okay, so what is the 250th even positive integer? The number 500. Very good. Does everybody agree with that part? Do you guys see it? Because look, the second even term is 4. The third even term is 6. The 250th positive even integer is 500. You guys with me on that part? Okay, good. So what do we want to do with this? We want to take the sum of the first 250 positive even integers. Well, it would be what? It'd be 250 over 2. The very first term is 2. The very last term is 500. So let's plug it into our calculators, right? That sounds good to me. Here's mine. So I would do 250 times what? Times 502. What would that give us? And then divide that finally by 2. So I'm thinking I'm getting the answer of 62,750. Wow, that's fast. 62,750. So the sum of the first 250 positive integers is 62,750. That's pretty sweet too. Okay, here you go. I'm giving you a sequence. The sequence is arithmetic. It goes 4 plus 9 plus 14. It stops all the way up at 99. How much is that going to be worth when you add it all up? All right. Yes, Rachel. 14 from 99? You did 99 minus 14? Yes, there. Okay, good. So Rachel just gave me a good way of doing it. I'm gonna offer you a different way. Okay, check this out. I'm gonna offer this to you guys. You know this. You always know this. Start with this. A sub n is a sub 1 plus n minus 1 times d. Where did I get that from? That's the explicit form for a arithmetic sequence. We have to have that one down. All right, we know that one. Okay, the term I'm looking for is this one, right? How much is it worth? It's worth 99, right? Equal, what's the very first term? 4 plus, I want n minus 1. And what's my difference here? My difference is 5, right? If I go up by 5s? Okay, so check this out. It tells me that 99 is the nth term. That's what that says. So I'm going to find the nth term, and that's going to tell me how many I have total, right? So here I go. I get 99 is equal to 4 plus 5n minus 5. So 99 is now equal to, what? 5n minus 1. So 100 is equal to 5n. So look, there's your 20, you guys. N must be 20. So however you want to come up with it, I always go this route because this is using the definition, right? But if you're taking advantage of the fact that it's linear, that's okay too. But you have to get the fact that there are 20 terms to move on. Because now you can have the sum of the first 20 terms is 20 over 2, first term which is 4, last term which is 99, and when you run that through the calculator you get 1,030 terms, or 30 as a sum. Who's heard of summation notation before? Yes, 2 people have? Awesome. Summation notation deals with this Greek letter. Who can tell me what this Greek letter is right here? Yeah. This is the letter sigma. Very good. The way that we say this is sigma. Okay. Summation notation is really, really nice because it allows us to shrink up everything that we want to say. Whenever you see this, the Greek letter E, or this, the capital letter E, and it's called sigma, whenever you see this, I want your brain to think of a phrase, and that phrase means you're going to add stuff, okay? Whenever you see the E, whenever you see sigma, you're going to be doing what? Addition. You're going to add stuff, okay? You're going to be doing add some stuff, okay? So let me give you an example of where we would use this. Whenever you add up anything, there are 3 pieces of information that you need in order to add things up. You need to know where to start, you need to know where to finish, and you need to know how to do it. Okay? So let me offer you this example here, okay? If I gave you 7 plus 11 plus 15 plus ... plus 203 plus 207, okay? And I wanted to find a better way of representing that sum right there. Okay? Well, here's what we already know. I already know that this is the first term, this is the second term, this is the third term. What term would this be here? A sub A. Can we figure it out though? Yeah, we can figure it out, right? Okay, let's go ahead and figure it out. I know that 207 is equal to the first term, which is 7, plus the quantity n minus 1. And what's my difference? 4. Very good. So 207 is equal to 7 plus, this is what, 4n minus 4, yeah? So 207 is equal to 4n, is that plus 3? Yeah? So 204 is now equal to 4n. So what is n equal to? N is equal to 51. Okay, good. Awesome. N is equal to 51. So what would be the explicit formula that I could use to represent this sequence here of 7, 11, 15, 203? Yeah, what would it be? 51. The explicit formula, it's just this. It's just this right here, right? 4n minus 2. So if you don't believe me, look. A sub n is equal to a sub 1 plus n minus 1 times d. First term is 4 plus, this should look familiar, right? N minus 1. And my d is 4, right? So I get 4 plus 4n minus... Oh, shoot, 7. Thank you. Because no one told me the explicit formula, so I'm making sure we get it. Okay? So it's just 4n plus 3. There we go. Right? It's the same thing here, but no one said it, so I want to make sure. Okay, so the way that we're doing this is we're taking 4n plus 3, right? You guys good with that part? If I plug in a 1, what do I get out? 7. If I plug in a 2, what do I get out? 11. If I plug in 3, what do I get out? If I plug in 51, what do I get out? 0. If I plug in 50, what do I get out? 0. Okay, good. So we can represent all of this using a sigma notation, and here's how we do it. We would start when n is equal to 1. We would end when n got to 51. And how we would do it is by taking 4n plus 3s.
So that's like how you write it?
Yeah, that's how you write it. It's a way...
Wait, that's how you write what?
That's how you write that sum.
So that's how you write the thing in the green?
Yes, the thing in the green box now becomes this right here in the thing in the blue box, okay? So, look what we've done. I've shown you this is where we start, right, with our inputs. You start here. What's the 51 represent? Yeah, no, where we ended, right? Yeah, and then what does the 4n plus 3 tell us? Yeah, that tells us how to do it. So you need these 3 things. You need to start, you need to end, and you need how you do it. All right? And where is the sum coming from, right? All of these sums right here are represented by the E itself, okay? Okay, let's figure out what this says, right? What does this say? This says we want the sum that n goes from 1 to 70 of 5n plus 3. What I suggest you guys do is I suggest you actually write a few of these out, okay? What is the very first term? What would it be? Yeah, it would be 8. Do you guys get that? Because if I plug in 1 and I get 8 out of this, right? Okay. What would the second term be? It'd be 13. Okay, let's skip up all the way. Where am I stopping, you guys?
70.
On the 70th term, right? And what is the 70th term of this thing? 353. Nice job, 353. Okay, so what would that sum equal? Well, we want the sum of the first 70 terms. It would be 70 over 2. First term, which is 8. Last term, which is 353. So the sum of the first 70 terms would be 12,635.
Oh, wait.
Wow.